All right. And one. Okay. So what's going to go in the middle? An oxygen. Are my hydrogens like this? No. They're in a V shape. Perfect. They're in a V shaped. And remember, oxygen has 2 lone pairs that are not part of bonds. Okay. These lines, you don't have to write this, but remember those are bonds. 1 electron comes from the oxygen and 1 electron comes from the hydrogen. Okay. So what is its shape? What do we call it? Bent. Perfect. It is bent. All right. So like I said, that is our last journal for this 6 weeks. So what we have going on today is our open nose quiz today, and then your journal test, which is Wednesday. So make sure that you get your journal together by then. On Tuesday, which is tomorrow, I will not be here because I'm having to do testing. So you need to watch a video tonight. It's already in Google Classroom. It's under daily work, the same place where your video was from last night. It's over solubility curves. And you need to watch that so you will know how to do the assignment tomorrow. It's very easy, so you should be able to watch it and then be able to do the assignment. Let's see what else. Retakes. About the only thing we have left for the retake is the molar mass and density quiz. And then if you're going to retake your gas laws test. You cannot retake your gas laws test until you correct it. So if you look at my tutorials up on the board, that's all the tutorials I have this week. You can't come in Thursday after school and tell me that I want to take the gas test. I want to retake it because I'm not going to sit there long enough for you to do corrections and then to retest. Too long. You have to do corrections ahead of time on that. So any questions on that? All right, so just make sure that you get done what you need to do during those certain times. All righty, if you will take out your Chromebook, then we will do the quiz. And then we will, but don't forget you need to watch that video because you'll be working on solubility curves tomorrow and you'll need that to be able to do your video. All right, we're just going to move through this part pretty quick. Water molecule has a bent shape with bond angles of 104 degrees. And remember that the higher electronegativity the oxygen pulls the electrons toward it, and that's what makes it have the negative side. So we've already drawn our molecule. 2 lone pairs. It's a polar molecule, so that means, bless you, it has a slightly negative side. That's a funny looking S that means a dipole, and a slightly positive side. The electrons have been pulled away from the hydrogen, so that's why they are positive, and they've been pulled toward the oxygen, so that's why it's negative. The bond that holds the hydrogen and oxygens together are the covalent, is a covalent bond. So that's your intramolecular bond. And then if I have a water molecule being held to another water molecule, that is your hydrogen bond. So that's your intermolecular. Bond. So covalent is within the molecule. Holding a water molecule to another water molecule is the hydrogen bond, which gives it most of its properties. So our hydrogen bond is a specific type of intermolecular bond, which is a really strong intermolecular bond as far as that goes. And it accounts for those properties that are listed in those 2 columns below. And we just went over a couple of them in the video. So all those listed, high surface tension down to water is the universal solvent. All of those are because of hydrogen bonding. So bless you. See surface tension because of hydrogen bonding, and that is the inward force or pull that tends to minimize the surface area. So this is liquid drops. So like if I spill water, if I spill a whole cup of water, it's going to spread out. But if you spill a small amount, instead of it spreading out, it first bubbles up. That's because of the surface tension. Also, this is the example where they give bugs or lizards walking on the water. That's because of surface tension. A surfactant is any substance that interferes with the, that should be a with right there, with the hydrogen bonding. So if you put a surfactant, which are usually things like soaps and detergents, then it's going to interrupt those hydrogen bonding, and then it's going to change the properties of water. Capillary action is when water will move up like a small tube on its own, because it's more attracted to the whatever the tube is made out of than the water molecules are attracted to itself. So if you've ever got blood taken, maybe just where they prick your finger and then they come with a really small glass tube and the blood just flows up it, that would be capillary action. Other examples would be the meniscus with water. It forms that little curve because the water is going to be more attracted to the size of the graduated cylinder than it's to itself. And also you see it with capillaries in trees or tree trunks. So adhesion or adhesive, y'all did these in biology. This is when H2O is attracted to something else. So that's what you would see in capillary action because it's attracted to the size of the little glass tube. Cohesion or cohesive means that water is attracted to itself. So you see that with surface tension, why it forms a bubble, because the water molecules are attracted to each other. All righty. Few other properties of water that have to do with hydrogen bonding, low vapor pressure. And vapor pressure is the tendency of water to change from a liquid to a gas, and that doesn't happen very quickly. It has to get to be a pretty high temperature for that to happen with water. We also know that liquid water floats when it freezes. Ice is going to be less dense than water, and that's also because of the way that it forms a solid due to the hydrogen bonding. And then some other things, all of these, just like the ones in that other two columns, these are due to hydrogen bonding. High melting and boiling points, high specific heat, and heat of fusion, which we'll use a little bit in this unit. And we'll especially use the fact that water is a universal solvent. It's able to dissolve so many different things. And one of the reasons that it is able to dissolve so many things is because it's polar. This picture just shows you a couple of ions. You can see if it's an anion, if it's a negative ion, the water associates itself so that the positive on the hydrogen side can be attracted to the negative. But I can also put in a cation, a positive ion, and then the water just flips itself around so that the negative can be attracted to the positive. So it'll do that with ions or other polar molecules. All righty. Moving on, and this is actually, this is the exact same part on your notes before. So it's a review. So we have two types of matter. We have pure substance, which is what we spent most of our time on so far, and then also mixtures. So under pure substance, we either had our compound, or an element. So element, anything off the periodic table, cannot be decomposed by chemical change. If I put two more elements together, then I get a compound, which can be broken back down into its elements. So now we're going to be spending more time under mixtures, specifically homogeneous mixtures, and another name for them is a solution, which is what we titled this unit. It means it has the same composition throughout. As compared to hetero, HETEROGENEOUS. I don't know if you'll get it right. So a heterogeneous mixture means it's not uniform throughout. So like something like trail mix would be a really obvious example. And under that, we had two different types that we've talked about before, either colloids or suspensions. And that has to do with particle size. Any of that ring a bell with y'all? It's been too long. Huh? Was it when we were Zooming? Is that what you asked? I don't think it was it that long? Yeah, oh, that seemed like a long time ago. Miss Corner was having another. All right, so solution, homogeneous mixture, same thing. We're tending to call them solution in this unit. It has the smallest particle size, and so it will go into solution or it will dissolve. An example of that would be a saline solution. You may know what a saline solution is. A contact, it is, but you know what makes it up? There's also, you can get an IV of saline. Yeah, it's salt and water at a specific percent. So saline solution is salt plus water. And so your salt is your solute and it will dissolve in water. So that'd be an example of a solution. Those do not scatter light. So that means it has no Tyndall effect. Tyndall effect is what happens if you, not with the solution because it's clear, if you shine a light through it, it'll just pass through that solution. But if the particles aren't dissolved and you shine a light through it, it'll bounce back at you. Like what happens with fog, that's considered a Tyndall effect. So we'll be looking at the solute and the solvent as we do our different formulas that we're going to be doing. Solute is usually there in the small amount and it dissolves in the solvent. Under heterogeneous mixture, the first one that we have is a suspension. And it has the particle size that is the largest. And so you may shake it up, but once you let it sit there for a while, then it's going to settle out. And an example of that would be muddy water or pink medicine, I call it. I don't know. Amoxicillin. Oh, I like the taste of amoxicillin. What will your parents give it to you when they take it out of the refrigerator? What do? They shake it up, because if not, all the medicine and sugar would be gathered at the bottom, and they'd be just giving you some water with a little bit of stuff in it. Some peanut butters, like the natural peanut butters that you have to stir, yeah, that could be an example of a suspension. Yeah, just a little bit of one. All right, under number 3, we have colloid, which those are intermediate particle size, so they don't dissolve, but they also do not settle out. They always have the Tyndall effect because the solid particles are just kind of floating around. So an example of this is fog, shaving cream, Delsum cough medicine. I don't know if any of y'all have ever taken. It's over the counter. It's like in a brown bottle, and you can almost feel the particles in it. Yeah. Oh, I think they do orange or oh yeah. Anyway, that's a colloid. So colloids are made up of 2 phases. They're made up of the dispersed phase, which is the colloid particle itself, and then the dispersing medium, which is just another name for the solvent. Colloids also have something called the browning effect, and that just means if you look at them under a microscope, you can see movement. If the little particles are not dissolved all the way, then they seem to be moving around. All righty. Okay. All right. Couple of pages here. All right. So Tyndall effect, we already talked about that. It's just the light scattering by the particles in a colloid, or maybe in a real fine suspension. We see it with fog, with jello. So we're going to take a closer look at solutions. What makes a solute dissolve in a solvent and actually form a solution? So the solution process is called solvation, not salvation like you get at church yesterday, but solvation. It's the process by which a solute dissolves in a solvent. So it's something is miscible, miscible. That means a solute will dissolve in the solvent. If something is immiscible, that's when the solute will not dissolve in the solvent. So like oil and water. You can mix some oil and water and it'll look like it's going to go into solution, but then you set it there for a while and they separate it back out. Aqueous solutions, which are mainly what we're going to be dealing with, means that the solvent is water. So saline solution is a good example of that. The salt is your solute and the water is your solvent. Tend to think of our types of solutions when we have a solid solute dissolving in a liquid solvent, but if you look at this box, you can have a wide variety of things. About the only combination that you cannot have is a gas dissolved in a solid. That doesn't happen. You can't get a gas into a solid. But you can have solid with a solid. That's going to be our different alloys. This is our air if we have gas and gas. Our carbonated drinks is when we have CO2 and water. So that would be gas and liquid. So the wide variety of different things that you can have, besides just this common one where you have a solid and the liquid. So whenever we're talking about what will dissolve in what solvent, we're talking about the rule of like dissolves like. And that's in regard to polarity. So if something is polar, it's going to dissolve something that is polar. If something is nonpolar, it's going to dissolve something that is nonpolar. So if we look at something and if we think about it, polar is charged because it has a slightly positive side and a slightly negative side. Ionic is also charged because it disassociates and forms positive and negative ions. So that means as far as looking at charge, those are considered alike. So polar and ionic will dissolve. And an example of that is salt and water. Salt is ionic, water is polar. Polar and ionic, because both of those are charged, will not dissolve if I'm trying to put it in something nonpolar. So if I'm trying to dissolve some salt in some cooking oil, that's not going to happen. Nonpolar will only dissolve nonpolar. Nonpolar doesn't have a charge. It's only going to dissolve other things that do not have a charge. So I can get butter to dissolve in oil. I got to mix it up a little bit to get it going, but it will dissolve. They're both nonpolar. Butter's not going to dissolve in water. So polar can dissolve. And I'm saying specifically about polar because that's kind of our big one because that brings in water. Polar can dissolve polar and ionic solutes. Remember, ionic is any metal plus non-metal or metal plus a polyatomic ion. Polar, that would be a little bit harder for y'all to know without me telling you that it was polar. When you take AP chemistry, we spend a little bit more time on that. All righty. So if we talk about solvation, what's going to form a solution and when it happens, if I have an ionic, away from me. If I have an ionic compound, it should not be same molecule. If I have an ionic compound and the water is a solvent, the first thing that's going to happen is dissociation of the ionic molecule is going to occur. So what that means, like if I have sodium chloride, it's going to dissociate into sodium plus chloride ions. So now those have a charge. This was neutral, but it didn't say like that in water. It disassociates. So then the water molecules can come and surround it, like we saw in our picture, and we say it is now hydrated. So that means a solution will form. If we look at polar covalent molecules, they're charged. So when I put them with water, dissociation will not occur. They don't form ions, but since they're polar, they still have oppositely charged poles, which means there's still something for the water to be attracted to. So we say that is molecular solvation. A solution will form. Now our last one where we have that a solution will not form is when I have a non-polar covalent molecule. It's not going to dissociate. It doesn't have a positive or negative side. There's nothing for the water to be attracted to. So the polar water is not attracted to the oil and there will not be any solvation. All right, so we're gonna stop right there. Tomorrow, like I said, tonight you need to watch your video over solubility curves. It'll ask you some questions, and then you will be looking at solubility curves, which look like this, tell you how much at a certain temperature will dissolve, and so you will need to be able to answer questions off of that. And that assignment is due at the end of class tomorrow. Yes, sir. What? Do I think water is red? I think it is.